All right. Hello, everyone. Welcome to today's Corundum developer meeting. So for today, I just have a handful of status updates. Let's see. We've got several different bugs that we've made some progress on. And the other main thing that I'm going to talk about is this new CMAC wrapper that I've been putting together over the past couple of weeks, over the past week or so, anyway. And then everything else is kind of carryover stuff that'll get hopefully knocked out pretty soon. All right, so the PCI Express bug, haven't done anything on that for a while because that's I basically backburnered that to work on a few other things. This one only seems to be rearing its head in combination with my updated descriptor write support. So until I get the descriptor write support merged, I haven't tripped over this issue yet in the mainline design, even screwing around with like the transmit engine sizes and whatnot. So this one's backburnered until we get that sorted out. Let's see. So then I have two different FIFO related memory inference bugs here that I'm going to talk about. So the first one is relating to the URAMs on Xilinx ultrascale devices. So in this case, the FIFO pipeline registers are not being properly merged into the URAMs. And I was really scratching my head over this for a while because they were being merged in where I was using URAMs and like the queue managers. And it took me a while to figure out what was going on here. And I finally figured it out after looking at the documentation. Go figure. The URAM cascade pipelines do not support clock enables. So when you use multiple URAMs that are, cascading into each other to build a large memory, they don't have clock enables in those cascade registers. And the read enables are also weird. Basically, you have to, the pipeline itself can't be stalled. And then the read enable has to be propagated down the pipeline and then drive the clock enable of the final flip-flop. Something really strange like that. I don't think any other RAM primitive really requires that kind of a strange inference template. Now, fixing the pipeline, so the pipeline itself stalling, there's not really much you can do about that besides add a FIFO for the pipeline to drain into. For handling the read enable thing, that's simple. You just set the read enable to 1, and then you don't need to do any screwing around with adding additional registers or driving clock enables or whatever. So the fix that I came up with is to add an optional output pipeline FIFO, or add an optional output FIFO that will drain the pipeline for the FIFO. So if you're building a large FIFO with like a megabyte or something worth of URAM, then you can turn this option on, and it'll give you a bunch of pipeline registers that don't have any clock enables connected or anything else, and that'll actually get merged in and work correctly. So yeah, yo dog, the FIFO needs a FIFO in order to work properly. So this one should be fixed now in the AXI stream library, and if that hasn't made it into the core Corundum code, it will pretty soon. It shouldn't change anything else about the FIFO. It's just there's a little bit of reorganization and then adding this output FIFO. All right, so that's bug number 1. Bug number 2 is something that the MLE has been working on, and I think we've discussed this the last couple of meetings. So it started out with seeing transmit packets with incorrect IP layer checksums, but only on Intel devices, and very sporadically, like 1 in a few thousand packets, something like that. The folks at MLE managed to trace that issue to the FIFO that sits between the transmit engine and the transmit checksum compute block, where those enable bits are somehow getting flipped. And after a bit more poking around, it seems to be a Quartus tool bug related to merging pipeline registers into the MLabs, because this is one of those Heisen bugs. When you try to debug it, it disappears, right? So if they connected a logic analyzer to the output register, I think, it would disappear. If they added a SYN preserve attribute to the output register, it would also result in the bug disappearing. So it seems like what's going on here is that when that register gets pulled into the MLabs, that it's it's not being handled correctly by the MLab, and it's not clear if this is like, you know, the MLab is documented to not work this way, but the tools are merging the register in any way, or if it's like incorrect timing data and it's actually some sort of a timing failure that's not being checked properly. It's unclear what the underlying problem is here, but I think Emily has done a little bit more work on this to try and come up with a workaround. It seems like using M20Ks instead of MLabs solves the problem as well. So I guess what we're going to do is report the issue to Intel and then probably roll with just a workaround for now. I'm honestly not sure what makes the most sense to do upstream. You know, if Intel fixes it, then we can roll ahead with MLabs. I think it's more of a resources question, because you want to use MLabs if you have like a very shallow memory, because it's 32 entries or less into an MLab. If you have more than that, then you need an M20K. But, you know, like other FPGAs, there's a limited amount of block RAM available. So if you're using a lot of memory, you know, maybe having those M20Ks available for other stuff makes more sense. So yeah, ideally, I think, you know, Intel would fix the bug, and then, you know, you'd be able to use MLabs where necessary. But for the time being, it seems like forcing things to M20Ks will work around this. So for everybody out there who's using Intel boards right now, that seems to be the situation. I guess we can circle back to this a little bit later, unless Emily has anything that they want to add about this right now. Joachim, Ulrich, do you want to add anything about this, or has that been a pretty good summary of what the situation is at the moment?
Sounds good, I think. So let's continue and perhaps talk later.
Yeah, all right. Sounds good. Okay. And then the other thing that I've been working on over the past week or so is a wrapper for the CMAC. And the idea is to provide kind of a similar setup to how I have a wrapper for the, you know, the 10 gig, 25 gig PHY plus the GT cores. Basically the same thing with the CMAC plus the GT cores. There's several reasons for doing this. One of the most important ones is that it allows all of the kind of integration level stuff to be centralized into a single module. And the annoying thing is, the reason I haven't been able to do that up until now is because the CMAC core, when you generate it, it has an internal placement constraint for the CMAC. So I had to figure out how to turn off that placement constraint, so you can actually instantiate, you know, multiple copies of the same core, and then potentially add placement constraints, or potentially just let the tools pick sites. So anyway, I had to do some finagling with TCL to figure out how to do that, but I managed to turn off that placement constraint. I guess the other thing I should mention is you can generate the CMAC core either with or without the transceivers. So without the transceivers, it's just a CMAC, and then you got to wire it up to the transceivers. So what I have set up right now is the core without the transceivers, so it's just a CMAC, and then with the placement constraint, you know, turned off. And then with that, then the transceivers can be integrated separately, and then that all packaged up into a wrapper module. And then you can drop down, you know, one of those per port. And then with this setup, what I can do is take the previous wrapper module that I was using for the 10 gig, 25 gig PHY, modify that to support operation with the CMAC. And then that gives us control over, you know, all of the GT control pins. So we can control the reset, power down, rate change. We can take iScan measurements, PRBS tests, all sorts of stuff like that with the underlying transceiver primitives. And then we can also connect up all of the control pins on the CMAC as well as the DRP interface. So you can change RSFEC settings. You can change like the interframe gap setting inside the CMAC. You can reset stuff. You can put it in the pattern check mode, you know, things of that nature. And even the statistics outputs can potentially be wired up to the statistics collection subsystem. So As of right now, I have kind of the data path portion of the wrapper working. I've tested it on in hardware on a couple different boards, and what I need to do is to integrate and test that on all the 100 gig targets, and then also to finish wiring up all of the control signals to the CMAC. I think right now I have it hooked up with the DRP interface, but all of the additional control pins need to be wired up. And then kind of a long-term to-do is to take all of the CMAC statistics outputs and wire those into the statistics collection subsystem. So that's not just packet transmit and receive counts, but also things like RSFEC error counts and things like that. So that'll be pretty useful when it's all done. But yeah, the idea here is that we'll be able to have, a somewhat more standardized way across all of the Xilinx boards, at least, for accessing the CMAC and changing some of these settings. So there were a couple of motivations behind this. I had a couple people asking about, how do we control the RSFEC settings? If you got to disable RSFEC in a particular setup, how do we do that? And when I was taking a look at the design, like, okay, could I make a little wrapper to bring out some of this stuff? I could do that, but there's a lot of pins to wire up in every single board. So I'm like, well, okay, maybe it makes sense to take a couple days and see if there's a better solution for this here. So hopefully over the next few days, I'll be able to get this finished off and merged into the main repository and tested on all of the current Xilinx 100 gig targets that use the CMAX. And I think that about rounds it out for the status updates for this week. I have more slides here in terms of some of the other stuff that I was working on previously. So like the DRAM integration, that should be in the main repository at this point. Obviously, there's still some more to-dos for this in terms of integrating with the DMA subsystem and the PCIe bar, but the main connections to the memory and the MIGs and the pass-through components should be there. Yeah, so I talked about all this stuff over the last couple of meetings. Let's see, is there anything else new here? No, I think the batch completion, right? Once I get a couple of these things squared away, then I'm going to get this polished off and merged back into the main repository. Let's see, I think that's about it. So I have the test data from this from the last time I was testing with that. Yeah, and then once that's done, then variable length descriptor support, right? I'll take that back to the to-do list for stable release, right? So let's see, what else do we have on this list here that needs to be done? I guess basically the variable length descriptor support, softcore, hopefully, and the checksum offloading. So getting things knocked out little by little. So yeah. All right, that about rounds out the status updates that I have for today. If anyone else has any questions or comments or things they want to discuss, go ahead, fire away. And then at some point we can turn it over to MLE for the rest of the meeting. That's how things usually go. Any questions or
Hey,
comments?
Alex.
Hey, how's it going?
This is Terry. I have a question about Corundum. I have an unusual use case. I would like to use Corundum without its existing PCIe and MAC. I just want to use like your
interface and without the MAC. Okay, so what would you be using then?
Your driver, your kernel driver.
Just the driver.
Basically, yeah, I would like to. So let me explain kind of who I am. So I am a trading firm, and I'm interested in Corundum mostly because we want a be able to just substitute into Corundum in to just drop in a NIC, so I can do things like packet capture and even simple things like ping. And the whole idea is that we already have an existing PCIe DMA and MAC. And I was just wondering if I could just reuse your driver and kernel and kind of just plug that in and use it as a physical function. Is that a use case you have envisioned? And is that something that is easy to do, or do I have to like rip the design apart to do that?
Well, I mean, what it really gets down to is what the what your NIC expects in terms of all of the descriptors and completions and what the register layout looks like and all of that.
Well, so I
So-
can make the Mac fit your design. I think it's more of the reason why I can't drop in yours is I'm using DFX shell to control build time. So all of the PCIe stuff is already frozen. PCIe and the Mac stuff is already frozen. So I just need a shim layer.
Are you using the Alveo shell or are you doing your own DFX?
I'm doing my own UltraScale Plus.
I see. Okay. Okay. Right. So one concern with using DFX to freeze the PCIe stuff is that you can't change the PCI Express vendor and product IDs. I mean, it's not really a huge problem, but that definitely affects how you can attach drivers to it because all the driver attachment is done based on those IDs. So
But
this
I can
is
hack
just-
your kernel module
right.
to
Yeah. You can change that. I'm just saying this is the reason that we don't, or one of the reasons that we don't support the Alveo framework, because you can't
I see.
attach a separate driver to it besides the Alveo driver. But yeah, if you're doing your own thing, then that's less of a concern. Right, but the issue is really how you're interfacing with the with the DMA engine and with the register space on the device. So it's like for Corundum, the driver was built in parallel with the hardware, because what the driver is doing is tightly coupled with what the core logic in Corundum is doing and how the DMA engine works and that sort of thing. So
you don't have like a nice one-to-one mapping of like a driver command to eventually an AXI streaming bundle into your kind of NIC proper.
I mean, sort of, I guess, but
Okay.
I mean, it seems like it's probably going to be quite different than whatever DMA engine that you guys have assembled. So, I mean, you could probably adapt it. It would probably be a good starting point. But
yeah, no, I was wondering if you have like
my guess is you'd have to make some pretty extensive modifications.
Okay, so that's not like there's not an adaptation layer. I kind of assume you did because you support different FPGA vendors.
Right, but the thing is, we're running the exact same HDL on all of them, and we're running a custom DMA engine, so we're not using any of the vendor supplied DMA engines. If we were using vendor supplied DMA engines, we'd have to have like a complete sub driver for each DMA engine, right?
Oh,
so it's
okay.
like we're not using the QDMA from Xilinx because that has a completely different descriptor format. It has a completely different register space,
Okay.
So
Okay, so it's
basically, if you're not using the Corundum's DMA engine and the Corundum core logic in your design, then you're going to have to rewrite a lot of the driver. That's
okay. And is that
how things work? So,
and is that like the bulk of the NIC, or there's no way to like detangle that from like the RSS and like the checksum stuff, and is that the rest of the stuff is actually fairly trivial compared to the DMA portion, is what you're saying?
I mean,
Okay.
that's all the driver does, right? So
Yes.
when you think about it, the driver, there's kind of several roles that the driver performs, right? One of them is it does all of the initialization and configuration and all of the what we call kind of the slow path stuff, right? And then it does all of the fast path, which is handling all of the data that's moved to and from the NIC. And
Okay.
all the fast path stuff is in terms of writing out descriptors and reading in completions that are going to be handled by the hardware or are written out by the hardware. And all that is entirely dependent on what the hardware is expecting in terms of what those descriptors look like. So
okay, yeah, no, this is great. I think you gave me a lot to think about. Let me take a stab at looking at the code. Maybe what I'll do is I'll take this offline, study a little bit more, and then I'll ping you on the Zulip chat to maybe ask you more questions. I don't want to take up all of your time here, but thank you for that. That's very helpful.
No problem. All right. Does anyone else have any questions or comments? If not, then I guess we'll turn it over to the folks at MLE. I just want to make sure that anyone else who has any questions or comments has an opportunity to ask that before MLE takes it away for the rest of the meeting, probably. Nope. All right. I guess we'll turn it over to MLE then.
Yeah, okay. Yet another
Right.
time. Yeah, regarding the various FIFO bugs, perhaps we're able to add a few more details. I asked David, our colleague, to also join. He looked at this FIFO problem in detail. All I would like to add is that at least with our custom board and our custom device, unfortunately, we get timing issues, rather minimal, but still negative timing number when we are using your modified FIFO, unfortunately. And also when using the Syn preserve thing.
So with the modified FIFO, with the current FIFO that I just updated, do you have some timing issues?
The modified version from end of last week.
Right.
So
well, we'll modify
there's another.
Are you talking about the some modifications that you made, or
no, your modifications?
right. Okay. So the updated FIFO that I have is causing timing issues. All right.
Yeah, unfortunately.
Take a look at that. Interesting.
So that's why we had to move to yet another solution, which was then to, well, let's see, does it help if we replace MLabs by M20Ks? And fortunately, that does the trick, or seems to do the trick for now.
Interesting. Okay, so it definitely seems to be whatever's going on is specific to the MLabs, and M20Ks are not affected. So if you force it into M20Ks, then it's okay. Right. So like I said, that's potentially a resource consumption concern to do that, depending on how many of these MLab, FIFOs there are. If you push all those to M20Ks, maybe you run out of M20Ks. But if it works and you have the resources, it makes sense to do that.
Yeah, at least in our current version of the design, we still have the Gen 3 PCIe Gen 3 problem to solve, which still causes a lot of timing issues. But for the current version using Gen 2, the M20K solution seems to be the solution for now.
Right.
So I asked David to join, perhaps to get in perhaps a little bit into the details, or update from our side what we have found. I think David, we are not yet necessarily at the point where we say, it has to be a tool bug, or
Hi, hi, this is David. It looks like a tool bug, yes, but I cannot finger point at it right now. So I think there's still the chance that the HDL description leaves some room for interpretation for the tool, and it's just by coincidence working on some technologies and not on others, but it looks like a tool bug. It's just we can't really say here is the piece of wrong logic or so, and so it's hard to be absolutely sure it's a tool issue. But given the fact that different memory technologies behave different in the same tool, kind of points to it.
Yeah, I mean, I think the real clincher is that adding Syn preserve changes the behavior, and that shouldn't be a thing, right?
Right.
That should only change, placement or whatever. If it's changing the actual functionality, then that indicates that the tool is doing something it's not supposed to do.
Yeah, and also switching from MLab to M20K, leaving the description, the HDL description, the same,
Yeah.
It's kind of the same thing. It shouldn't change behavior. But yeah, it's just we don't. I'm not sure we will get there. It could be a timing problem as well. So maybe it needs some post implementation simulation to really say this is where it's wrong. But I'm not sure we will get there.
Well, I mean, since we've isolated that FIFO, it might make sense to put together kind of a minimal example, right, of basically just the FIFO with a little bit of logic to drive it. And you can have, you know, 2 copies of the FIFO, one using MLabs, one using M20Ks, or one using MLabs without the preserve attribute, the other with it, or something like that. Something that you can drop on the device and test and run through, you know, post placement, post routing, whatever simulation, to see if you're seeing the same behavior in simulation or if this is just in hardware or whatever. So that would help with the debugging, and then you could hand that off to Intel as well, perhaps.
Yeah. Right, because at first sight, there is logic generated to control the enable signal of the output register. So it's not completely ignored that this needs to be controlled, but the question is the logic correct? Is the logic incorrect? Is it a timing problem? So yeah, hard to say at this point.
Yeah, my current theory is that it's we're seeing like some sort of a timing issue where we're getting like a runt pulse or setup violation or hold violation or something on the control signal, and then that's causing the issue. So why we're getting that problem, I'm not sure. Either, you know, something is wrong about how the tools are doing the timing analysis, or the timing parameters for the MLabs, you know, at least on that pin, are wrong, or, you know, something along those lines. So
Yes.
Because just looking at the kind of the frequency of those bad packets that you get, it's a relatively small number of packets that are transferred, you know, incorrectly, or that have that enable bit flip-flopped. So
well, but that might be misleading because the majority of packets actually has it enabled. So
well, that's
the
a good
chance
point.
to
And it's
get
not
it
just
enabled
enabled,
for
but it
a-
has the same settings that are
Right.
getting handed off. Right. Okay.
Yes. So it doesn't necessarily mean that the FIFO wouldn't have more errors if the pattern were different. So
Right. Okay, that's a good point. Well, that's definitely an argument for making a kind of minimal toy example, because then you can try a few things and see, does this happen every time, or is this only, you know, 1 in 10, 1 in 100, or whatever. So
yeah.
all right. Well, that'll definitely be useful if we can figure out a little bit better what's going on there, and then hopefully get Intel looped in as well.
Well, another point just came to my mind. For now, we are using Quartus 22.1, I think. The .2 version was broken anyway because of some PCIe issue.
Right. So the PCIe issue, I think, is fixed in 22.3. I downloaded and installed 22.3, but haven't had a chance to do anything with the Intel devices in a while. So yeah, that'll be on my list to check soon. I don't know if they fixed any other issues in, I think they might have fixed some between 22.2 and 22.3, but yeah, that's a good thought. If we check this under 22.3, it might fix the problem. Maybe, not sure.
Yeah, maybe one of the first things that Intel asks us to do. It's typically a reaction to these reports.
Yeah, and the other aspect was that I guess we talked about that last time, or the one before that, I don't know, about these bad, obviously, apparently bad checksums in the RX path. I guess we also keep that in mind. Uli, you brought that up, since most likely the logic kind of is the same we think. I guess we didn't look at that, but I mean, that was rather unlikely. You said, Alex, that you got bad Eric's checksums in really low numbers, and we've only we also see them in lower numbers, even sometimes no bad Eric's checksums seem to be there. But we have to keep in mind that probably that issue is also related to exactly the same thing here.
It could be, yeah. Well, I mean, if you force everything to use M20Ks, have you checked for that again?
No, not
not yet?
explicitly.
Okay.
We detected these RX back then. We detected the RX checksum issue with a different machine, a faster machine, not our regular testing machines. And so we've not looked at that again.
Okay.
But kind of the question is, we assume that the RX logic, which is calculating the checksum, is more or less the same.
Yeah, it's very similar. I mean, in the RX direction, there's a bit less logic because it basically just computes the checksum, but it doesn't have to do anything to insert the checksum or anything into the packet. It's just doing the computation. But yeah, the part that's actually computing the checksum should be doing the same thing. Yeah.
I also have a question. Have you checked with ILA how the signal was coming? I mean, is it repeating the same burst, or is there something different, or is it skipping some part? I mean,
so in the RX
what
direction,
kind of?
for
Yes,
bad
yes.
RX checksums.
Yes, in bad RX checksum.
I don't think we've done any real thorough investigation of that yet.
Yeah, no, not yet. Yeah.
So the other problem with using an ILA for something like this is you got to be able to trigger off something, right? Because you're not going to be able to use the ILA to look at every single packet. So
or at least you can use a hex stamp maybe to see in upper parts if you are not throwing everything which has IP checksum error also.
Right. Yeah. So I don't know if the ILA would work here, but yeah, we can definitely do debugging kind of at the driver level, maybe. I mean, I think at this point right now we're just looking at it's like a network stack counter in Linux that's reporting these checksum errors. So how you get from that back into the driver and back up to the FPGA, that's a potentially a more complicated problem. But yeah, so this one definitely needs some more investigation. But what the technique is going to be to figure out what's going on here is a different story.
The first problem is to trigger it, since it seems to be really, really unlikely. That was easy in the TX case. It was really easy to trigger it.
Yeah. But in the RX case.
And the trigger condition was also kind of easy because the pseudo TCP header checksum was always the same in our case, since we have one TCP stream. And so we just triggered on that checksum value, that known value, because as soon as the TX checksum module has done the calculation again over the same data, including the checksum field, then the original checksum value from the pseudo header is the result. So that was the trigger condition, really easy one. I don't know what to trigger on the in the RX case. That's most likely a harder one.
Yeah. I mean, I guess you could just validate the checksum. and you can see if we're seeing, invalid checksums, and if we aren't seeing any invalid checksums, and that indicates there's something between the checksum computation and the, which is probably what's going on here, right? Because if we're seeing invalid checksums, then why would you be getting bits flipped just in the checksum field? Seems like you'd be getting some bit flipped somewhere else. But if we're not seeing any bit flips, basically it's just the checksum that's included in the not the packet itself, but the completion record that's wrong, then that doesn't really narrow things down very much. You have to compare what's in the completion record versus what the actual packet checksums to. So yeah, triggering on that one is tricky. So you got to
Yes,
be a bit more
it might
creative.
have to be stored somewhere before deciding if there is error or not. This is, I think, yes.
Well,
I
guess
mean,
potentially with some
you
of the stuff,
cannot know if the packet has error or not until awaiting the end.
right? Yeah, and that if you're trying to use something
So
like the
you have
ILA, then
to
that doesn't really
store.
work, right?
You have to somehow store and decide to log if it has error or something, and when it has error, you should send somewhere else, maybe maybe in application part there you can make something to store the packet until the end of packet comes, and when end of packet comes, and when you understand that there is an error, and you can send somewhere else, maybe. I'm not sure.
Right. I mean, in this case, the Linux network stack is detecting the packets as having bad checksums. So at that point, yeah, you can see that the packet that was the problem, but that doesn't necessarily help because you don't know where the computed checksum came from, right? The invalid computed checksum, because it seems like what we're seeing here is not data corruption of the packet itself. So having the packet isn't necessarily all that helpful, because it's this sideband, metadata that's the computed RX checksum that's incorrect. So working that metadata back to where the incorrect computation is going to be the trick. So I'm not sure if there's a nice way of doing that, unfortunately. Let's see. Yeah, so I guess the first thing to do is to get all of these FIFO memories in M20Ks and just run it again and see if we're still seeing those checksum issues.
Yeah, we'll definitely have a look. I guess we are anyway about to do another bring up round of another boards, and while checking these boards, perhaps we see it again or we don't see it anymore.
Is this another revision of the same board?
No, same revision, but another batch.
More of them. Okay.
I think the error also occurs when the speed is low, right? Packet rate is low. I mean, when you send a low packet rate, you still can catch the error, right?
I don't know. The test case was a full speed one.
Oh.
So I can't say if it happens with
if
lower rates.
If at low rate we can log actually all packets, maybe, but at high rates, yes, of course.
Well, in our case, we are not that high, just 10 gigabits. So TCP
right,
dumping is possible, at least to RAM disks. In the FPGA with an ILA or something, it's going to be very hard.
Yes, with ILA, yes, you're right. It's hard to trigger.
Yeah, that's.
But you can dump, I think, yes.
Yeah, that's always
I'm
one of
not
the trade-offs
sure.
with the ILA is that you kind of need to know what you're looking for and be able to come up with some sort of a real-time trigger condition. Otherwise, it's not all that useful. Unless you happen to get really lucky. Sometimes maybe you run it and you catch the bug.
Maybe brute force for one day. And if you are lucky.
Well, I guess they use that kind of technique with network monitoring sometimes, right? They don't capture every packet. They capture like 1 every 10,000 packets or something like that. So maybe with the ILA you could do that, right? You just the bug has to be high enough probability.
Yeah.
I think in this case it's low enough probability where that wouldn't work very well.
Yeah.
Oh,
Well,
what I was
okay,
gonna say is
let's
that
see.
I guess another possibility could be to generate a bunch of packets. And so instead of running like iPerf, where all the packets are generated on the fly, but something more like TCP replay, where you generate a set of packets, you know what the packets are, you know what all the checksums are, and then you could just send those repeatedly. If you can hit line rate with that, which I think with jumping through the right hoops, at least at 10G, that shouldn't be an issue. If you know what all the checksums are, then you can see, are we seeing all of these checksums or are we seeing some other checksum? And then if you're seeing some other weird value, then you can try to trigger on that with the ILA. And that could potentially give you some insight into what's going on here, right? It's like, are the incorrect checksums that we're seeing, are those like coming from the wrong packet? Like, hey, we got the checksum of the last packet instead of the checksum of this packet, right? That could be one thing to check for. Or if we're seeing a totally random checksum, then you can say, okay, well, we're only sending these 8 packets. And if we're seeing a 9th checksum that's totally different, well, then at least you can trigger on that in the ILA.
We sometimes use a similar technique, like we send a pickup of many gigabytes from one side and capture from the other side, and we compare the files.
Right, yeah. That could work.
Other
well with storage.
idea, so we could just create a loopback on the Mac side and then have a more or less a FIFO looping back the TX computed checksums to the RX side and compare them.
I guess you could do that. So let's see.
Because it's just a couple of packets that are in the full pipeline, right? So it's not a lot of entries that we need to just forward the checksums.
Right, but it's just the checksums are not looking at the same things is the problem. Right, because the TX in the TX direction, the checksum is going to cover one portion of the packet, right? And then it's going to be inserted
That's right.
into the header somewhere. Versus on the RX, it checksums everything after the Ethernet header.
Right.
But I guess what you could do, because you don't care about the checksum, is just cook up the TX checksum range so it computes the same thing as the RX checksum. I guess you could do that. And then, have it not insert those or something. Yeah, I mean, you could do something like that. It's a question of what's going to be more work. I'm thinking, going for some sort of TCP replay based setup with either some cooked up packets or just, something along those lines is probably going to be simpler because that doesn't require any hardware modifications. Because you could probably do that and then just get some insight into, what you can do that, and you can potentially have, make a couple of simple modifications to the driver to print out some information about the packets as well as that, sideband, computed receive checksum. And then you can look at that and compare, okay, when you do get a bad checksum value, what was it? And what was it in relation to some of the packets received, immediately before and immediately after, just to see if we're getting some random, new checksum that we've never seen before, or if it's potentially some sort of a FIFO issue where we got, the previous guy's checksum or something like that. seems like it shouldn't be all that hard to try. It wouldn't require any hardware modifications. And then if you're seeing some, ninth unrelated checksum, okay, well then you at least have something you can trigger your ILA on.
That's right. But maybe at first see whether this pops up anyway, and with the move to M20Ks, and maybe that's already gone and we're fine on this side.
That sounds like a good step 0, right? We changed the FIFOs. All right, let's see if that fixed anything. Oh, and maybe also see if it builds on 22.3, right? And see if these issues are present there. Because maybe,
we'll
maybe
do that.
Intel fixed something.
Yeah, with the original version, unmodified, meaning using MLab. And yeah,
I think we should be able to just quickly check the build results, because one of our colleagues just did a sweep run
right.
with at least in this area of the design without modifications. So he should be just able to open up one of them and see if the output registers have been absorbed.
Well, I mean, output registers absorbed or not, it's possible that the issue is something else, and that some other change can be made that allows those registers to be merged and actually work correctly.
Yeah. Okay. So
Right.
then we have to rerun the thing.
But if you have an image built, then it's just, hey, you drop it on the board and you check to see if it works.
Exactly. Yeah. So that's just build time.
Right. Yeah. Yeah. It's like it depends on what the actual underlying issue is with this. Like I can think of several possible explanations, and depending on what it is, the appropriate approach to take at the tool level is different, right? I mean, if it's like a timing problem, well, maybe just fix the timing constraints, and then it works fine. If it's actually some sort of silicon problem, and the functionality is wrong, and no matter what you do from a timing perspective, it's not going to fix anything, well, then you just can't merge it. So yeah, that's, I think, one of the reasons for getting a little toy design, kind of minimal functional thing put together that we can hand off to Intel, because then they can take a look at it and figure out what's going on and figure out what the most appropriate fix is. Or maybe they can just say, hey, you're doing this wrong. And then we can fix the code, depending. All right. Is there anything else to discuss for today? Is that everything that you guys wanted to discuss, Joachim and Ulrich?
From my side, I guess that's it. Joachim?
Yeah, that's it.
Right.
We already have moved to our next problem, so stay tuned.
Oh boy. No preview on that yet. This is also something related to Corundum, or this is something more related to your customizations?
No, this time it seems like it's software related.
Okay.
But the question is, why is this only happening with our custom board? So yeah, need to investigate.
Well, okay. Hopefully you guys don't need to spin another hardware revision.
Yeah, would be good. Yeah. Okay. Yeah, that's it.
All right. Well, does anyone else have any questions or comments or anything they'd like to discuss? Going once, going twice? Nobody? All right. I guess we will go ahead and adjourn the meeting for today. thank you to everyone who had the time to drop by and tune in. And I guess we will go ahead and meet again in 2 weeks on November 21st, I think. Same time. No more time changes for for a while, hopefully. All right.
You can never know.
Well, I don't know. Maybe other time zones in other countries, other parts of the world have different daylight savings schedules. I don't know. Anyway, talk to you guys later.
Sounds good. Bye.
Thank you. Have a nice day. Bye.
See you next week. Have a nice day.
Thanks
Yeah.
all of you. Bye.